Okay, today the new concept that we introduced was the hydraulic jump. Hydraulic jump is how the flow transitions from a supercritical flow to a subcritical flow. So here we have a depth transition that goes from Y1 upstream of the jump to Y2 downstream of the jump. And the question is, what's the relationship between Y1 and Y2? What we're saying is that the Froude number upstream, Froude number at location 1 is greater than 1, the Froude number at 2 is less than 1, which can also be thought of using a depth ratio. You can say that Y1 over YC is therefore less than 1, and Y2 over YC is greater than 1. That's a C. Okay. So we have this relationship that holds across the hydraulic jump. The question is, how can we develop a relationship between Y1 and Y2? When we considered flows over bumps or through constrictions, we conserved energy. But in this case, energy is lost in the hydraulic jump. So we need to use some other principle to relate 1 and 2. Because the hydraulic jump occurs over a short distance, there's very little friction applied along the bed. And in fact, we can apply momentum conservation on a control volume as shown in blue. The forces acting on this control volume are the force of pressure from the upstream face, the force of pressure from the downstream face, and that's it. So if we write down our momentum equation, we find that the sum of the forces in the x direction is equal to, we're going to assume steady flow, so that term is 0, plus the sum of the fluxes of momentum, which would be rho vx vi dot ai. We have two faces, face 1 and face 2. The velocities through each can be written as Q over A for those faces. And then the pressure forces, I'll just note that the force of pressure from the left is equal to the pressure at the centroid times the area, which is equal to 1/2 gamma times y1 times y1 times the width. Pressure from the right would be subscripts 2. So our force balance then becomes the force of pressure from the left minus the force of pressure from the right is equal to inflows minus outflows. So it's negative inflows minus rho v1 squared a1 plus rho v2 squared a2. Making the substitution for the pressure forces and dividing by the width, and noting that Q is equal to the flow per width, so that velocity times depth is equal to Q, allows us to rewrite this equation as 1/2 gamma y1 squared minus 1/2 gamma y2 squared is equal to minus rho Q squared over y1 plus rho Q squared over y2. Now this equation may not be particularly obvious how to solve it. Again, I mentioned this in the lecture today. You factor out the y1 squared minus y2 squared on the left, combine the two fractions on the right. That allows you to cancel a factor of y1 minus y2, and then you can define a quadratic for y2 over y1. The end result is that y2, I'm going to rewrite that, y2 is equal to y1 times 1/2 times the square root of 1 minus 8 times the upstream Froude number squared minus 1. That relationship defines the transition across the hydraulic jump. Now, to assemble this into a general understanding of channel flow, I'd refer you to the lecture notes from today, where we talked about when hydraulic jumps are necessary. It's basically when supercritical flow needs to adjust its energy in order to get past an obstacle. To do that, it has to transition into a subcritical state and then evolve downstream in anticipation of the obstacle. So hydraulic jumps become required when there's a downstream obstacle blocking supercritical flow. That supercritical flow has to transition to subcritical, and then it can adjust to get past the obstacle.